Hello, students. This brief tutorial will concisely address for us reaction mechanisms. So, what is a reaction mechanism? Well, a reaction mechanism is our best attempt at as chemists using our understanding of other chemical reactions and observations of the reaction that we're taking a look at. And we're trying to really predict, how do the reactants truly interact? Which bonds are broken? How maybe are the reactants, and what specific reactants are coming together to break bonds and form bonds? It's our prediction. It's what we imagine is happening on the particle level. And just a reminder, most processes, even if we imagine making a peanut butter and jelly sandwich, getting dressed in the morning, taking a shower, it requires more than one step. The same for chemical reactions. So let's look at an example. This is our example reaction. So this is what we put into our reaction chamber and we produce this. And experimentally, we've determined that the rate is second order in the NO2, zero order in carbon monoxide. So we would sit down and, knowledge again of other reactions and the observations that we take of this overall reaction or the complete reaction and predict a mechanism. All right. These are called elementary steps. So a mechanism has at least two elementary steps that take us from the overall reactants to products. For this, it's proposing that two NO2s are needed to react to produce these. And of course, there'll be an associated rate constant with this reaction per the temperature. And then the creation of the NO3 is what reacts with the carbon monoxide. Different reaction, different rate constant. So it's just generically saying K2. If we take a look in the first elementary step, we are making NO3 that then is being reacted. If we say, okay, this is happening and this is happening, but overall, we're making this and then reacting it away. So it is not going to add, the elementary steps add to yield the overall reaction. This species that is produced and then reacted and does not show in the overall reaction is called an intermediate. Mechanisms have at least two elementary steps, but they can have many. The molecularity is the number of species, reactants that are colliding, reacting to make products. An unimolecular step or molecularity, an unimolecularity would have only one reactant. A bimolecular has two. Both of these are bimolecular. The creator of this mechanism wanted to be sure that we did not miss. If we would have written 2NO2, we may have missed that it was bimolecular, that really it is the NO2 reacting with the NO2 that creates this. So that's why it's writing that instead of collapsing it like we normally do. Termolecular would be more than 3. The most common is bimolecular because just in nature, the probability is not that great for two reactants to collide with sufficient energy and proper orientation. But once we start to get more than 3, that is just hard to get the 3 molecules to come into contact exactly at the right orientation. So this is pretty rare, quite honestly. Okay, something that is quite nice is I'm just going to go ahead and erase these little marks that I made. The rate law of the elementary step comes from the molecularity, or in other words, comes from the balanced equation, reactants. Only for a reaction mechanism, only from an elementary step can we use the molecularity to derive the rate law. Never, ever for the overall reaction. We need to apply the method of initial rates or graph. From an elementary step, for example, this first elementary step, the rate law of this first elementary step would be K. And if I want to go ahead and use this one because it's designated as that, it doesn't matter. We could write NO2 to the first, NO2 to the first, which of course we would collapse these to be NO2 second. So per this first elementary step, the rate law shows NO2 to be second order. The rate law of the second elementary step would be K2, NO3 to the first, because coefficient of 1, CO to the first, or first order in both of those. Okay, now I want to speak for a moment about catalysts. So imagine that this is the overall reaction, and it's predicted that these are our elementary steps. So this is actually what happens on the particle level to react ozone into oxygen. So first, do we see any reaction intermediates? Species that are first produced and then reacted away. So a reaction intermediate, I produce CLO and then it gets reacted away completely. Otherwise, O, and then I'm reacting away monoatomic oxygen. So those first seen as product and then reacted, reaction intermediates. But there's something else that cancels out. Chlorine. Do you see, one chlorine is reacted and then produced. Chlorine will not show up in the overall reaction, but it's first seen as a reactant and then as a product. Chlorine is acting as a catalyst. So catalysts actually do play a role and undergo a chemical transformation, but they're reproduced. We predict, because remember, a catalyst is unchanged. We add it, but then we get it right back out. And our prediction is it accomplishes what it accomplishes because it does take a role in one of the elementary steps, but then it's produced. So just to show, all right, so these will not show up in the overall reaction, but if I would add these, so everything on the reactant side, I have two O3s, and then take a look, it is making 3 O2s. So that is one way that a reaction mechanism can be held true. A reaction mechanism has to pass two tests to be considered possible. The first test, the elementary steps must add to give the overall reaction. But then the next thing, the rate law of the elementary steps must match the rate law of the overall reaction. Okay, so if we take a look at this example problem, we're given, this is our overall reaction, and experimentally, it was found to be nitrogen monoxide second order. We're asked, could this be a possible mechanism? Our two tests. First, do the steps add, and it doesn't mean we have to do this one first, but we'll go ahead and do this because I just went over it. Do the elementary steps add to yield the overall equation? All right, first thing I'm going to get rid of are reaction intermediates. So I produce this, gone. Oh, N2O, gone. All right, so adding up 2NO plus 2H2 yielding N2 plus 2H2O. Ah, wonderful. This matches the overall reaction. Pass the first test. Next test. Does the rate law of the mechanism match the overall rate law? One of your steps will be the rate determining step. You will be told the relative speed. And we just use the term slow and fast. We give the designation of slow to the elementary step that has the lowest rate, the slowest. And then all the others are called fast just because they're not the lowest. So it's very unlikely that both of these are, happen at the same speed or the same mole per liter second, whatever. But these will be the designations. Well, a process is only as fast. It can only be as fast as its slowest step. Think about, trying to get into an amusement park and you have to go through the turnstile. So people all line up and you're really at the mercy of how many can, or scan their ticket or whatever else to get into the venue. So that is just an example. So we take the rate law of the slow step because that is really going to set the pace of the reaction. So we know we can get the rate law from the elementary step just from the molecularity. And it's going to be some rate constant times the reactant raised to the power of the coefficient. Okay, I don't have any other species. I don't have to check the rate laws because my slow step doesn't contain any reaction intermediates. And take a look, this matches that. So the answer I would give is this is a possible mechanism because one, the elementary steps add to yield the overall reaction, and the rate law of the reaction mechanism, again, from the rate determining step or the slow step, you will be told these, equals the rate law of the overall reaction. If one of these would not hold true, it's not a possible mechanism of overall reaction. Now, we've seen reaction diagrams, usually just reactant to product, but we can also have a reaction diagram that shows us the elementary steps. If we take a look, the largest hill, and we'll talk about this from the energy difference between the reactant and the tip of this peak, that's activation energy. So if we take a look, that is definitely the greatest height of hill. That's going to be our rate determining step. And that does match the slow step. So each of these peaks, this would be the first elementary step. This would be the second, and then this would be the third. So overall, we start with this and get this, but we think it happens in these three steps. All right, so we've gone through terminology. I've worked through some examples. So in your packet, on page 28, here's an example. Please take a look. And And on page 29, examples. An example problem, but it actually proposes 3 different mechanisms. I'm going to now place the answers for these, but please try this on your own. Think through it. I'm going to show my answer. So if you want to go ahead and pause now. Okay, so there's my work. And then page 29. I'm going to show the answers. And the final answer, only mechanism 3. And I hope you can see why. Okay, now there is another situation that we're going to take a look at where the mechanism involves an equilibrium step, where the slow step is preceded by a step that is fast and an equilibrium. That will be considered next. So for now, we want to just get really, really good at the foundational ideas. Thank you.